Right. Sorry, it took me a couple minutes to get my technology set up. Actually, before we show that, I want to remind you that your test 1 on chapter 5 is today and tomorrow, and that is it. Remember that there is also a review assignment in my math lab that will be excellent study material. So your test is the very top item, the thing that says it's due on the 15th by midnight, essentially. So there's your test. I'm actually giving you 120 minutes for this first one. I said 90. I'm giving you a little more time with this one just to be nice. You never know when technology will cause an issue, like my math lab is just chugging along. And then again, the review under your homework is right after the 5.8 section, chapter 5 review. No due date on that. I'm gonna leave it open all semester because those reviews will also be good for the final later. You don't have to do the review, but it would be very, very helpful. I've only seen one student so far complete the review. I said complete, not attempt. I know one other student has attempted it partially. But please, if you have the time, work on the review before you work on your only attempt on this test. Remember, this is a no notes, no book, no calculator test. You're not supposed to be using any of those materials. And I'm being very lenient for now when I'm not making you have your cameras on you while you're testing, because I think that that's a barrier of entry. But if I find that I have to do that, I will start doing that. It's possible I have to do it for the final no matter what. But for now, if we can all be responsible, then we'll continue to do it this way. But it is pretty easy to tell when there's funny business going on, so no funny business. Okay, so for now, we're going to continue working on stuff that is not related to the first test in chapter 6.1. This is quite a long section. Verifying trig identities. So we're going to have 1, 2, 3, about 5 more, 4 more, 5 more, something like that to do today. And then we can get into the next section finally. So remember, trig identities are equations that you must make the left and right side match. You will do this by using various trig properties seen over the last chapter. An identity is only verified once the sides match. And I've said for the next test, it's possible I'll do an explicit paper or pencil, maybe just like 1 question or 2 question with these, because I think that the homework problems, which would look like the test problems, kind of push you a little bit too much in the right direction. You should have to do this from scratch, like I'm doing in the lecture, and understand that while the homework problems push you through one particular way, there's dozens of ways to do almost any problem. So the things that you need, the tips and stuff that I gave you that generally work, turning things into sines and cosines, using your Pythagorean identities, one of these 3, the first one being my favorite because quite often I usually go ahead and turn things into sines and cosines, so then the second 2 aren't even necessary. Factoring, and so far we've seen a GCF. We haven't seen either of these 2 yet. Hint, wink, nudge. Combine your fractions or split your fractions or clearing your fractions, just changing the appearance of your fractions. If you've got separate ones, maybe combining them helps you. If you've got them combined, maybe splitting them helps you. If you want to get rid of the fractions completely, that's my personal favorite thing to do. You can just clear them in the ways we've seen in examples. Using even and odd properties, we haven't seen, and I don't know that I do have an example involving it, but that's if you had something like, if you had, say, the sign of negative theta inside of your identity, you could in the next step say, well, that's negative sine of theta. Or if you had the cosine of negative theta, there's a negative in there, you could say, well, that's even, so it's just the cosine of theta. Excuse me. And I got to do that one more time, but I'm not. All right. I will say this one isn't used nearly as frequently as the rest of them, but it still comes up every now and then. Multiplying top and bottom by a conjugate. So if you've got a fraction that looks like maybe 1 over 2 minus cosine of theta, you could multiply top and bottom by 2 plus cosine of theta. That's what it means to do a conjugate, top and bottom. And it makes some cool things happen quite often. You can cross multiply if it's a fraction equal to a fraction. What we commonly do is we're only dealing with one side and then maybe deal with the second side if you kind of get stuck on one side. And we said starting over, sometimes you'll hit a dead end and you just got to start over. And while I haven't demonstrated that in class, and I won't demonstrate that. It has certainly happened to me countless times. When I was a student, it happened to me as many times as it's happened to y'all, or will happen to y'all probably. As a teacher, it's less frequent because I've had, tons and tons of practice, but I still have to start over every now and then. All right. So we got up to example F. Okay. So we're up to G then. G. Do I have enough space? Nah, that's not gonna be enough space. So let's go down here. G, and I probably need to hit enter some more. Yes, I do. Sorry for the setup. We'll get there. Tangent of 2 theta. And I'll be a little cleaner with my thetas now because there's a 2 in there, plus the cotangent of 2 theta, all divided by the secant of 2 theta is equal to the cosecant of 2 theta. Admittedly, all these 2 thetas, it doesn't even matter. It doesn't affect this problem at all. I could just have tangent of theta plus cotangent of theta over secant of theta equals cosecant of theta. Again, these 2 thetas do not affect this problem at all, but only because every single one of them is a 2 theta. In fact, you could use a substitution. You could say let x equal 2 theta, and that's tan x plus cot x over sec x equals cosecant x. However, let's just pretend for a second, and this will no longer be accurate, but if this was a regular old theta, then this is now a significantly different problem. And in the next section, we're going to learn these things called double angle formulas, which maybe then we would have to start applying. So I'm just getting you used to seeing the 2 thetas, but again, admittedly for now, there is 0 effect on them, but make sure you bring them along. Okay. So what do I want to do? I'm trying to decide. I have an alternate approach and then a longer approach. Let's do the longer one first. So let's say some people just really like splitting fractions. Me personally, I would end up multiplying and clearing the fractions. So I'm just describing a couple things that work. So this is one thing that I could do. I could multiply both sides by secant of 2 theta, and then secant of 2 theta, and then the fractions would be gone, and you could go from there. That would be one thing, and maybe that'll be my alternate approach. But for now, what I'm going to do is say, I'm going to split the fractions. I'm a student that says, I don't like these fractions combined, so I'm going to split them. So blue for change. Tangent of 2 theta. Now again, every single one of these is going to be a 2 theta. If it's a little sloppy, I apologize. But every single inside is this thing. It's never going to change in this entire problem. So I've clarified that. Over secant of 2 theta, and then plus cotangent of 2 theta over secant of 2 theta, then equal to, not really much we can do with cosecant of 2 theta, so let's leave it alone. All right, well now I see I don't see sines and cosines anywhere, and maybe you can deal with the problem this way, but most people really like to switch to sines and cosines in a situation like this. So blue for change. So this tangent of 2 theta is going to become a sine 2 theta over cosine 2 theta. Again, that was this. But it is over the secant of 2 theta, and secant is 1 over cosine of 2 theta. Then the plus sign, which didn't change, so black. I guess the fraction bar didn't change either. That fraction bar was this one, but I want to leave it that way. Cotangent is the reciprocal of tan, so cosine over sine. So cosine of 2 theta over sine of 2 theta. Then all over, so this fraction bar originally is this one. Now that secant of 2 theta is still 1 over cosine. And then we have that equal to cosecant of 2 theta. Now you see this, these fractions inside of other fractions, and maybe it makes your brain hurt a little bit, but when you have a fraction divided by a fraction, that's just multiplying by the reciprocal. I think I have that note written earlier, don't I? I don't want to write it again. Yes, I do. Whenever you have a fraction divided by a fraction, you can change it to the old school division look, and then ultimately getting you to, you change the division to multiplication and flip the bottom. So whatever's in the bottom here is going to get flipped, and then you'll change everything to a multiplication. So take the middle step if you have to. If you don't have to, then you don't have to. It's up to you how many steps you show. So this will be sine of 2 theta over cosine of 2 theta, which this part technically isn't changing. So I'll go to black. And then I'm going to switch this to times. So this big giant division bar is now the times. And then this part that was in the bottom is going to flip. So instead of 1 over cosine, it's cosine over 1. Then we'll do the same thing for the second fraction. So again, the top doesn't change. Cosine 2 theta over sine 2 theta. But now this division by the bottom becomes a multiplication by the reciprocal. Like so. And then that will be equal to the right-hand side. Equals is always black. Cosecant of 2 theta. Now check this out. You got a fraction multiplication with common things top and bottom, so they cancel. You got a fraction multiplication with common things top and bottom, right? Did I write something wrong? No, I didn't. There we go. We're good. I got confused. I confused myself for a second because I was thinking both would have a cancellation, but they don't, and there's nothing wrong with that. So again, these cosines will cancel. I just don't want to leave that on my notes permanently, so I'm erasing it. So now that first bit is just the sine of 2 theta. Now you can write it over the 1 if you want to, but if it's the only thing, we generally don't do that. We might have to make it a fraction again later. It's up to you. And the plus sign. Now we said nothing actually cancels here, so we have to stack it. Cosine times cosine is cosine squared 2 theta, and the bottom still actually has that sine of 2 theta in it, and the right-hand side is still cosecant of 2 theta. Well, I'm not seeing anything off the top of my head, but I am seeing fractions still. So when you still see fractions, you go, one student might say, I want to clear the fractions, and that student would say the only LCD factor is this, so they multiply all 3 bits by it. And another student might say, well, first I split the fractions and I feel like I'm at a dead end, so maybe now if I combine them with sines and cosines, maybe that would help. That would be fine. It would be perfectly fine. And in fact, because in the alternate example, I am going to do the LCD and clear them, I don't want to use that method here. So I'm going to pretend like I'm the student that forgets you can just get rid of fractions and equations. So they'll say, all right, I want to combine the left side by getting an LCD, which the only denominator is the sine of 2 theta. So you'll multiply this one top and bottom, and again, I'll erase this in a second. Sine of 2 theta, sine of 2 theta, so that you'll get an LCD. So I'm going to stick with the fractions. Not all students remember that you can get rid of them. All right, so what that gives us now is sine squared of 2 theta over sine of 2 theta plus cosine squared of 2 theta over the sine of 2 theta equals cosecant of 2 theta. Now we're actually going to do the combining part. So I split it and then I combined it. It feels weird that I did that, but check out what happens when you do. You get sine squared plus cosine squared all over sine. Right-hand side hasn't changed the whole time. It's not going to start now. Now you might say, well, why didn't you change it into 1 over sine? I could have. There's nothing wrong with that. And in fact, I probably should have, but I know that a lot of students only like messing with one side. So that was why I chose to. Again, an alternate method. I've already described like 16 different ways when you consider probability theory and multiplying. Well, guess what this thing right here is? That's a Pythagorean identity. It's 1. So, Pyth, and we get 1 over the sine of 2 theta equals cosecant 2 theta. Well, wait a minute, 1 over sine is cosecant. So let's just change this thing into sines and cosines as well, which again, you could have done at the very beginning. There was no reason not to. From this point on, I could have just written that as 1 over sine. This could have been 1 over sine, 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 and we would be done now. So we get 1 over sine 2 theta equals 1 over sine 2 theta, QED, FIN, DONE, LOL. So that wasn't a short problem. It required a decent amount of algebra and arithmetic, as well as knowledge of calculus, excuse me, trigonometry. I don't know why I just said calculus, pardon my French there. We turned things into sines and cosines. Admittedly, the splitting of this fraction here, admittedly, you didn't have to do that, but I know that some people would have tried it, which is why I'm trying to do things in ways I wouldn't necessarily do them, in the effort to say, hey, there isn't just one method. Then we turned everything into sines and cosines. And again, I didn't actually do it on the right-hand side because I said we're just going to deal with the left-hand side until the end, kind of going with that idea of only working with one side and then eventually both. But you certainly could have made that right-hand side the 1 over sine initially. Then we handled our division of fractions. Then we reduced what we could. Then we got an LCD, which we said here when we got our LCD, we could have instead just multiplied everything by sine of 2 theta, and you pretty much would have been done at that point because sine times cosecant cancel because they're reciprocals. If you don't recognize that, then you change the cosecant to 1 over sine, and you definitely see the canceling. Either way, ultimately, you get down to here. So the alternate version of this, I'm going to write a little, let me just zoom in actually. That gives me more space in theory. Where's my problem? Where's my problem? Tan 2 theta plus cotangent of 2 theta over secant of 2 theta equals cosecant of 2 theta. What some people might have said is, all right, well, go ahead and multiply by your LCD, which is secant of 2 theta. So you do that on the left. You do that on the right. So that these secants cancel and you get tangent plus cotangent is equal to secant cosecant. Then what I would do is turn everything into sines and cosines, which would give us sine over cosine plus cosine over sine equals 1 over, and you can actually just dump both of these in the same bottom of the fraction. If you want to share them, I'll show you what I mean in separate steps though. That's 1 over, the secant is 1 over cosine, then times cosecant is 1 over sine. But when you have 1 over something times 1 over something, you can just squish them all together and say it's 1 over cosine times sine. Well, darn, because we switched to sines and cosines, we ended up injecting fractions back into this equation. I hate fractions in equations. I'm pretending to be that student, which I don't hate. Hate's a strong word for me, but I still would clear them because it makes it a lot easier. So we would do another LCD, but this time the LCD is the cosine times the sine. So sine 2 theta cosine 2 theta. And when you multiply that by all the bits, dang, I ran out of room. that's okay. You get, I'm just going to write sine cosine times that fraction plus sine cosine times that fraction equals sine cosine times that fraction. Sine over cosine plus, and then cosine over sine equals, and then that's times 1 over cosine sine. And then you cancel what you can. The cosines are gone from the first one, the sines are gone from the second one, everything's gone from the right-hand side one. Sine times sine is sine squared. Cosine times cosine is cosine squared. And that's just a 1. The left-hand side is 1, the right-hand side is 1, and you're done. Is that method simpler? I don't know. Depends on how you roll. It depends on if you remember that you can clear fractions like that in equations. If you forget that fact, then you're probably going to have a problem that, or work that looks more like the first example, the first version of the example, where you deal with these multiplying by reciprocals and everything. And don't think that you're gonna, oh, I'm not doing the problem this way. I'm gonna do it the second way Mr. Beckner showed me. Don't think that means you get to avoid dividing by fractions, changing to multiplying by reciprocals. That will come up multiple times in this chapter that you can't avoid. I promise that. Again, do I actually care how you get these things done ultimately? No. The point when you get to calculus would be to see this ridiculously ugly left-hand side and go, I might be able to break this down. I might be able to simplify it. Let's try this. Let's try that. Let's try this. Let's try that. And then at the end of the day, you figure out, yeah, I can. And the whole thing's just 1 over sine, which I could make cosecant if I wanted to. And at that point, you can then apply a pretty simple formula, which calculus is just formulas. But what people mess up in calculus is remembering all the algebra and pre-calc 1 and pre-calc 2 that is necessary for the in-between of the formulas. Calculus is easy. It's the algebra that's hard in calculus. All right, now that we have just done that one to death. Sorry, I couldn't find my problem. Sine of x, we're going to switch to x's now, just for fun, over cosine of x plus 1. I know my definition of fun is sick and twisted. Plus cosine of x minus 1 all over sine of x equals 0. Now, admittedly, this is a problem where doing that multiply top and bottom by conjugates could actually help you. It could get you to the answer. I'm not going to do it that way, and I'm going to stop doing alternate approaches because it just gets ridiculously time-consuming. So again, that one could actually help you finish this problem. Another person might say, well, why don't I move one of these to the other side? Then I've got fraction equal to a fraction, and I can cross multiply. That would also be a good step. That would be a good process as well. So that would be a second alternate method. What I'm going to do is I'm going to say, I see fractions. I do not like fractions in equations, so I'm going to find my LCD, which is just the product of those two things, sine of x times cosine of x plus 1, and then I'm going to multiply all the top bits by it to clear fractions. So we go sine of x times cosine of x plus 1 times that first fraction, then plus, give myself a lot of room, times the second one, and then on the right-hand side, times the 0. So times sine x over cosine x plus 1 times cosine of x minus 1 over sine of x. And I'm leaving an error in here temporarily while you catch up and write. Okay, so where's my error? It's right here. I have a product times something with multiple terms, not in a parentheses. So make sure you wrap it. And then what do? We cancel. Cosine x plus 1 is going to go away from the first fraction. Sine of x is going to go away from the second fraction. And anything times 0 just all is going to go away from the right-hand side. Again, I don't want to leave the slashing in the notes permanently. So now what we have is, again, the cosine x plus 1 canceled there, so that's just sine times sine, which is sine squared, then our plus. We canceled the signs here, which leaves us with the pair of parentheses being multiplied, cosine plus 1, cosine minus 1. I'm not going to try and do too many steps at once, so I'll leave it like that for now. But we will be ultimately, foiling that out. Next step. And then equals 0. Because anything times 0 is 0. So let's FOIL that right-hand side. Not right-hand side. FOIL the pair of parentheses here. Cosine, we'll leave the sine alone, so that's sine squared. Plus. FOIL, F, cosine times cosine is cosine squared. The outer, the cosine times the negative 1 is a negative cosine x. The inner, the 1 times the positive cosine x is a plus cosine x. Then the last, 1 times negative 1 is negative 1. And then we still have our equals 0. Combine like terms. Negative cosine plus cosine. They're going to cancel. Just like every single solitary time in math, when you multiply conjugates in a plus b times an a minus b, the outer and the inner always cancel. That's also the reason why that whole multiplying top and bottom by conjugates here, that would have been a little more work, but it still does ultimately get us there for very similar reasons. So again, these are opposites and cancel. So all we have left is the sine squared plus the cosine squared. Then these cancel, then there's the minus 1 equals 0. Now you might say, ooh, this will be Pythagorean if we move the 1 over, and you certainly can move the 1 over, but you don't have to. Because if you move the 1 over, you still have to change the sine squared plus cosine squared to 1 to actually be done. So instead of moving it, I'm just going to say, use Pythagorean on the sine squared plus the cosine squared. So again, this right here is just positive 1. So that's a 1. But we have a minus 1 after it, which is 0, and we're done. Yay. Remember, it never matters what the left and right sides are at the end as long as they match. That's all you have to do. So again, many alternate ways you could have done this. The main primary one being multiplying tops and bottoms of each fraction by conjugates, but the conjugate of the first one will be cosine of x minus 1. The conjugate of the second one is a little weirder to figure out because it's only a single term. You could say that's sine plus 0, so you multiply top and bottom by sine. A lot of people think it's negative sine. It can get the job done, but it'll make it look a little weirder in the process. So that's the reason I didn't use that alternate approach. You could have just also gotten an LCD and combined the fractions. So you would say, all right, this first one's missing the sine of x, so multiply top and bottom. That's what's different by sine of x. Then the second one is missing the cosine of x plus 1. So you multiply top and bottom by that, the 0 you leave alone, and then you would have these with an LCD so you can squish the fraction together at that point, and you would end up doing the Pythagorean as well. You would be foiling this top, you'd have a sine squared here, you end up with this would end up being the top of the fraction, it's just you'd also have a bottom, but it wouldn't matter because as long as the tops match, the bottoms match, ultimately. Okay. But I think this was the most efficient way to have done this. So I talked through some alternate methods, just didn't fully show them. Next to last one, I promise. Sine to the fourth of theta minus cosine to the fourth of theta equals 1 minus 2 times cosine squared of theta. So these are the largest exponents we've seen so far, but don't let that intimidate you. You learned how to factor things with bigger exponents back in Pre-Calc 1 and Algebra 2 or wherever you learned your factoring. If you didn't learn factoring, I'm terrified for you. I don't know how you got to trig, and I know I've said that before. I say the same thing to my Pre-Calc 1 students. Again, I'm not here to teach factoring. But because we see these bigger exponents, it's definitely probably best to start with factoring. Now, as a reminder, difference of squares is a squared minus b squared equals a plus b times a minus b. So if you had something like x squared minus 9, it ends up being x plus 3 times x minus 3. But what if you had something like x to the 4th minus 9? The b in this instance is still 3. I shouldn't have written it that way. That was a terrible idea. There we go. The b is still 3, so a plus 3 and a minus 3 are there, but the a is no longer x because you got to think about, well, what squared would give me x to the 4th? Well, we hope that after several bits of practice back in Pre-Calc 1, you realize that x squared, when squared, turns into x to the 4th. So that's what happens when you have bigger even exponents. You just half them when you're using this difference of squares formula. Now, if you don't like this shortcut, what this is a shortcut of is the substitution method. So if you prefer to say, let u equal x squared, then u squared is x to the 4th, and then you'd say, all right, well, x to the 4th minus 9 is actually u squared minus 9, and then you go, oh, I know how to factor that. It's u plus 3 times u minus 3, but you got to go back to your original variable where u was x squared. I don't care how you're getting the job done. I care that you can get the job done. This is just some reminders on factoring, whether it's a substitution method or a more advanced shortcut with practice that you eventually understood. This is a difference of squares. It doesn't matter that it doesn't say x and a number. It's something squared minus something squared. So if you're thinking about what the a and the b are, they're going to be a sine and a cosine. But not just sine and cosine, because these are 4s. They're sine squared and cosine squared. So the factored form is sine squared of theta plus cosine squared of theta times sine squared of theta minus cosine squared of theta. The right-hand side, this is not a difference of squares. I'm not going to try and factor that. Maybe it's factorable. It's factorable using irrational numbers, but I generally don't need you factoring with irrational numbers in this course. Because you have to say that b is square root of 2 times cosine. Don't bother with that. That's too weird. Okay, so then back in pre-calc when these were x's and y's, you would have gone, well, okay, well, the first thing's a sum of squares, so you can't factor it. But the second thing, this here, is factorable even further. Sine squared minus cosine squared is once again literally a difference of squares, and it looks a lot more like the basis of it. So your a would be sine and your b would be cosine. But the first bit is prime because of the plus, unless you want to use imaginary numbers, and we're not ready to mix imaginary numbers with trigonometry. Spoilers, trigonometry, these sines and cosines are literally imaginary. They have imaginary numbers in them somehow. There is a relationship there, but we're not going to get into it. It's some crazy stuff. So I'm going to take the second parentheses and I'm going to factor. So I'm going to leave the first one alone. And you might say, well, wait a minute, that first one, I know that first one. You could go ahead and fix that if you want, but I'm just doing one thing at a time. I could have done it first as well, and I didn't mean to leave it in blue, so just, I want consistency. Sine squared plus cosine squared. But the second set is changing to sine of theta plus cosine of theta times sine of theta minus cosine of theta. The right-hand side I still haven't messed with. Now it's this thing right here, sine squared plus cosine squared. And again, you could have gone ahead and fixed it up earlier. You could fix it at the same time as factoring. I just don't want to do too much at once. That is Pythagorean. So that's just 1. This whole bit is just 1. So then times, I'll leave the spacing so you can tell what went to the 1. This blue ink doesn't change, so now it's black. Sine of theta plus cosine of theta times sine of theta minus cosine of theta. Right-hand side has not changed yet. Now, we didn't really need to write the 1 times part. I mean, I liked to show that this turned into the 1, but ultimately in the next line, you're not going to see the 1 part anymore. Now, I said the right-hand side is factorable using irrational numbers, and we don't want to do that. We're going to hit a dead end. In fact, right now, I'm not seeing a way to progress this further without unraveling. So this is going to feel like a previous problem where we split a fraction, then combined it, or maybe combine it and then split it. So even though I did recognize that this bit was factorable, it didn't help me. It did not help me factoring this part. It definitely helped me factoring the thing with fourths, because then I was able to get rid of half of this thing, really, just making that a 1. But this pair of parentheses multiplying, I don't really see a way that I can progress without just refoiling it out. So you might say, well, that was mean, Mr. Beckner. Why didn't you just tell me to leave this? Because guess what? When you're doing it on your own, you might see that and think, oh, let's factor it. You just factored earlier, so why not factor again? So it was a pointless step, and I know you think I'm mean for doing that, but you don't know that necessarily, and I wouldn't know it necessarily until I get to this point and feel the dead end. But I'm going to say, I don't want to start back from the very beginning. I know at least this was pretty good. Maybe just leave this unfactored. So I'm not going to show the foiling. You literally see it up there earlier. It's sine squared minus cosine squared. That's then on the right-hand side, it's not changing. So black, oops, black, 1 minus 2 cosine squared of theta. Now here is why this is better than the previous line. I only see sine squareds and cosine squareds. When you only see sine squareds and cosine squareds, it's a good probability, there's a good probability that you're going to use Pythagorean identities somewhere. A sine squared plus cosine squared equals 1. And you don't have to do it that way. You don't have to rearrange to try and see sine squared plus cosine squared. You certainly can. But you could just say, all right, I'm going to turn the sine squared into 1 minus cosine squared, or I'm going to turn these 2 cosine squareds into 1 minus sine squared. And that's the way I'd done it in the past. So this time, to change the game up, again, you could change this thing into 1 minus cosine squared. And you'd only want to change that because then you'd have cosine squared, cosine squared, cosine squared. Or you could change both of the cosine squareds to 1 minus sine squareds. This is my least favorite option because, first of all, there's a minus in front of them, so you'd need parentheses. Second of all, I'm doing 2 changes instead of 1. But it works. So here's what I'm going to do. I see there's cosine squareds on both sides, so I'm going to go, I don't like those on both sides. Let me just move them. Which one do you want to move? Do you want to move the left one, or do you want to move the right one? I don't really care. I'm going to move the one on the right. So I'm going to add 2 cosine squared to both sides. If you prefer, you could say I'm going to move the one on the left, and then you would just add a single cosine squared to both sides. So we get the sine squared of theta. Now that's going to be a plus, negative 1 plus 2 is positive 1, so plus cosine squared of theta equals, the 1 doesn't change. Those 2 things canceled. And I know, you know, by now, you better know that's Pythagorean. But remember, in terms of formal proofs, we're not done until we do this. Boom. There is a significant amount of variance in these types of problems, but that list of things to try I gave you is pretty much all inclusive on, if you try these things, eventually you'll get there as long as you learn your trigonometry, as long as your algebra skills aren't super rusty, as long as you learned the proper algebra before you got here and didn't forget it. which is why I said rusty earlier for some of us. And I completely understand rusting up. If you don't use something for a year or 2 years or 3 years, you're going to forget it. I can't tell you how much math I forgot, but I can go back and relearn it pretty quickly because I've seen it before. It's just a matter of scraping off that rust on the brain. I haven't done math from grad school in over a decade, and I don't remember 99% of it at this point. But if I had to, for some reason I was going to start teaching grad school, I could go back and relearn it probably over a month or two, because that's way, way, way complicated. All right, let's stop derailing. J, last one for the section, which I know you're ready for. Now, I need to warn you, though, this is not the last verify an identity, though, because in the next couple of sections, we're going to learn more properties of trigonometric functions, like these double angles and half angles and a few other things. And what that allows us to do is to have these verifying identities where we would need to use those as well. Also, when we get to solving equations, not just verifying them, finding out, well, all right, what angle makes this true? Because we can have equations where it's only certain angles that make it true. It's not that just the left side and the right side are identical, but under a cloak. So we'll need all of those properties there as well. All right, last one. Sine squared of theta times 1 plus cotangent squared of theta equals 1. All right, now some students might say, I don't like dealing with cotangents, so I'm going to make that cosine squared over sine squared. That'd be perfectly fine. And after you do that, you would need to distribute, and then you would have a Pythagorean identity to use. However, that's kind of going with the same way I've been doing things over and over and over. So at this point, I just want to try something a little different. I want to see if we can recognize what this is, this 1 plus cotangent squared. That is one of the Pythagorean identities. Scrolling, scrolling, scrolling. This would probably be quicker. Oh, that was weird. I pulled my mouse up and it went down. What is happening? 1 plus cotangent squared. There's a Pythagorean identity. It's cosecant squared. Now again, if you don't have this one memorized off the tip of your brain, I guess, then that's when you go, let's make the cotangent cosines over sines, then distribute that thing in the front, and then you'd see your Pythagorean pop up. But if you remember these three or are really quickly able to produce them, then it will actually save you some time. So that highlighted bit is actually a Pythagorean identity. We said that 1 plus cot squared is cosecant squared. So we'll leave the sine squared alone. Now I don't need the parentheses anymore since that's going to condense to a single term, and that's cosecant squared, and then equals 1. Now some students will recognize, ooh, sine and cosecant are reciprocals. So if you have a sine times a cosecant, they cancel. A sine squared times a cosecant, they cancel. Some students will just go ahead and do that, and then you're done. If you don't recognize that, if you're not that student, then you go, okay, I'm not seeing what's happening here. Maybe you'll change to sines and cosines instead, which means you'll change your cosecant to a 1 over sine. But since it was cosecant squared, it makes it 1 over sine squared. And now we can absolutely see the implicit cancellation I mentioned, that the sine squareds cancel and the whole entire left side is just a 1. So we get 1 equals 1, and we're done. Quod erat demonstratum. That which was to be demonstrated has. I could spend 3 or 4 months just doing these. Fortunately, we definitely don't have 3 or 4 months to do them. This is what a lot of trig students struggle with. Students that might do pretty good in the first chapter will hit this and they'll start struggling because they won't know what to do initially, so they just stop and they don't do anything. Don't do nothing. Try something. Okay, well, I see this cotangent. Maybe I just turn it in sines and cosines. Mr. Beckner said that's usually a good idea. It's usually a great idea, in fact. And just doing that might put you a little closer. And again, you might hit a dead end and you hit your head on the desk or whatever it is you personally do, and that's not a suggestion, don't hurt yourself. Whether or not I've done that in the past. Cry a little, whatever you have to do, and then you say, all right, let's gather ourselves, let's regain control, and let's look at the list of things to try and see what would apply there. Because you never know what can put you down the right path. Now, the students who do really bad in chapter 5 are going to do really bad on this as well. Now, it's not as much of a case of remembering the sine of 30 degrees is this and the cosine of 45 degrees is that, and building the triangles and doing a smart trig class and your quadrantals and all that, but it is still a lot of things discussed from that previous chapter. So if you didn't learn your Pythagorean identities, if you didn't learn your even and odd properties, if your algebra is rusty and you don't remember how to handle fractions by combining or clearing, or the idea of conjugates, there are a lot of different things that you can stall out on. And that's why this is a trig teacher's, honestly, one of their favorite types of problems, because it wraps so many different things into a nice, gift wrap package. Now, obviously on a test, I'm not going to give you 20 of these. These are kind of in the same regard as the making a graph, which I promised you'd only see like 2 on the test, which I kept my promise. You would only see 2, 3, maybe 4 of these on a test, and if it was 4, several of them would be very short. We've seen short ones like J and A and B, I want to say. We've also seen some really long ones. If I was going to give you a really long one that there's no way to make it short, even with tricks, unless it's a trick I don't see, I'd only give you one that's going to take you a solid amount of effort, say like I or H, or in particular G. But I can still give you one like that. All right, so that will close out 6.1. Waiting, there we go. So let's do a new document. Let's close the old one, and this will be 6.2. Getting pretty good at not saying the wrong sections because of my notes from the various texts I've had. I have 8.2 originally, then that's crossed out, and then 7.4 was the second phase, and that's crossed out. Now we're at 6.2. That's just from us changing books and editions, which is quite frustrating, especially when, quite honestly, when we change from the previous edition to the current edition of this textbook, there's almost no difference except they reordered the chapters and sections. I might have seen 1 or 2 examples in the book that are different, but there's no new material. It's just a way of making money. The sum and difference formulas for trig. All right, so let's do left a line, enter a bunch, get some space so we don't goof up later. Okay. The sum and difference formulas. And there are going to be times in this course where I give you a formula and then we prove it. There's going to be other times where I give you a formula and I say, just take the leap of faith with me, just trust me, they are true. Generally speaking, you can go to your textbook and find the proofs of them, and it might make your brain hurt a little bit, which is why I skip them. Or you can go to the internet and find them. But it's generally just, if I don't do a proof of a formula moving forward, it's because it's extremely time consuming. So we're just going to use these 4 formulas that I'm also going to condense into 2 formulas. We're going to just take this as the gospel. We're going to trust me. We're going to take the leap of faith. And yeah. All right. So without further ado, our formulas, which in a horribly mean trig class, you would have to memorize when you're in calculus. They don't, most calculus teachers don't give you cheat sheets and formula sheets, so you still have to have them memorized then. I did, half a decade of math, and I was never allowed to forget pretty much any formula from trig, pretty much any formula from calculus. All right, cosine of, now I'm going to introduce 2 new Greek letters. They are alpha, which kind of looks like a certain fish, and then beta, which looks like a B with an extended bottom. The back of the B kind of looks like it's dropped down. So This is alpha. This is beta. And no, this has nothing to do with Walking Dead. And I'm going to go ahead and give you the third one, gamma. So this is like our ABCs. So gamma looks like that fish, but we have it facing down. It looks like a fancy Y, kind of. So that's gamma. And I don't know why I didn't capitalize that A, not that it matters at all, but there for consistency. ABC, alpha, beta, gamma. Your homeworks quite often will just use upper and lower case letters to distinguish between a side length and an angle. But this is the classic approach. I honestly wish the textbook didn't do it that way, and my math didn't do it that way. I wish they used alpha, beta, and gamma more, because when you get into calculus, that's probably what you're going to be using over and over and over and over and over and over. All right, so again, this is like saying the cosine of x plus y. That's all this is. Don't let the funny Greek letters confuse you. Cosine of x plus y. That's all that says. All right, so this formula is cosine of alpha, or x, times the cosine of beta, which we're calling our y, then a minus symbol, and then the sine of alpha times the sine. Let me write that a little more space accurate, times the sine of beta. There's no 2's in here anywhere. There are no 2's anywhere. There are no 2's anywhere. My alphas consistently look like 2's. It's really hard for me to make that alpha look proper. That's a better image of the alpha, but I've just got this horrible habit that I have tried to correct. It always ends up swinging a little bit more. It's not that exaggerated, but it is a little exaggerated. So again, there are no 2's in this. The cosine of alpha plus beta. So if you think you've got an angle that you could break down to a sum of 2 different angles, then you could find the answer to the cosine of the original combined angle by splitting it up this way. Or alternatively, if you had this in some goofy equation, you could say, hey, I know that that is just cosine of alpha plus beta. It can go either way. I will say we're usually going from the left to right side, but there are times when we go from right to left. All right, next formula. Cosine of alpha minus beta. Again, let me just fix my spacing a little bit. There we go. So this is going to look almost identical. In fact, I'm going to write all the identical pieces out of the gate. So cosine, cosine, and then sine, sine. Can you guess what the only change here is? Good guess. That's a plus. These are very much the same formula. The only teeny tiny little change between them is when you have a plus between them, it's a minus between them in that version when you're kind of making this look way worse than originally, but with purpose, trust me. And when it was a minus between them originally, it's a plus. So if you had me for pre-calc 1 or developmental math, when I go over the sum and difference of cubes formulas for factoring, they're 2 formulas, but I always write them as 1 ultimately. So here's the combined version I'll do in blue. The cosine of alpha plus or minus beta. So this plus or minus is not the plus or minus from a quadratic formula that's saying both things happen. This is an either or scenario, kind of like when we were talking about reference angles in different quadrants, that we'd say the cosine of 240 degrees is the same as the cosine of 60 degrees, but with a plus or minus. All right, so it's equals cosine alpha, cosine beta, then the other part is sine alpha, sine beta, and then the symbol that goes here you might think is going to be the same thing. You might think it's going to be plus or minus, but the problem is the plus case here dealt with the minus here and vice versa. So you actually use a minus plus symbol. Again, these have nothing to do with saying both things are happening. It's a one or the other. So if you originally have a plus, then you pick the minus. Or if you originally have a minus, then you pick the plus. But this is an awesome way to condense these 2 formulas together because it feels like less memorization. So if you have a sum or difference of cosine angles, it's cosine, cosine, sine, sine. The cool thing about this one is it actually doesn't matter the order you write the alpha and the beta because a product The order doesn't matter. Same thing here. You can actually write the second one first for these. Notice I said for these. And it won't mess anything up. It's just you got to remember plus leads to minus or a minus leads to plus. Okay, so the next pair of formulas we have, so this was the combined version, is the sine formula. Oh, yes, black. So the sine of a first angle plus a second angle. So these don't go paired together, cosines and sines, they're actually paired in opposites. It goes sine, cosine, cosine, sine. It goes sine of alpha, cosine of beta. Now this one, the SIGNs, the pluses or minuses, they actually correlate directly. This one goes plus, and then it goes cosine of alpha, sine of beta. So the cosine formula has cosines and sines paired together. The sine formula goes sine and cosine. So sine of alpha, cosine beta, and then this one is the exact opposite. So if you had sine of alpha in the first, it's cosine of alpha in the second. If you had cosine of beta in the first, it's sine of beta in the second. Yes, you can swap the order of these two things. You could go sine beta, cosine alpha. Nobody cares if you swap those two things. That's really the only thing that you can swap. And that would just be for someone that always wants to go sine, cosine, sine, cosine. If you have a subtraction between them, it has the exact same similarity previously, in which the sine cosine pattern doesn't change, but the minus, or sorry, the plus becomes a minus. Yeah, that got a little sloppy, sorry there. Let's try that again. Cosine alpha, sine beta. So the sine pattern is sine, cosine, cosine, sine if you keep the alphas and betas ordered. So if you just want to write a condensed version of this, sine of alpha plus or minus beta, again, no twos, is equal to, it always goes sine, cosine, and then cosine, sine if you're keeping the alphas and betas ordered. Plus led to plus, minus led to minus, so this stays a plus minus. When I memorize these, I memorize the blue versions, not the black versions, because it's a 2-for-1 in both scenarios. 12 minutes, 13 minutes, okay. So that was the combined. You can either memorize 4 formulas or you can memorize 2 formulas. It is up to you. You can either memorize the blacks or the blues. No bruising from the black and blue. So what exactly are these used for? What are these helpful for the most in general moving forward? The sine of 15 degrees, the cosine of 75 degrees, the sine of 105 degrees, the tangent of, let's see, 195 degrees. When you have angles, so we've learned back in chapter 5 how to extensively deal with 30, 45, and 60, as well as all their multiples, as well as all the quadrantals, 90, 80, 180, 270, 360, etc. But we said without a calculator, the only things that we could actually process are when we're dealing with 30 degrees, 45 degrees, 60 degrees, and then multiples of 90 degrees, as well as all other multiples of 30, 45, and 60 placed in the specific quadrants, 2, 3, and 4. With these formulas, we will now be able to use that information, but also now be able to do things like the sine of 15 degrees, because we can turn 15 degrees into 2 different angles being added or subtracted, and we would want to try and use things like 30 and 45 and 60 because we know how to evaluate those trig functions. We can't just say, oh, the sine of 15 degrees is 1 over square root of 3 or anything like that. There's no 2 simple triangles to memorize to base that off of. And if you said, well, why not just add those 15 degrees and 75 degrees and all other stuff to a unit circle memorization? If that's the way you're doing things, if you're memorizing the most giant, ridiculous unit circle in the world, be my guest. I have absolutely no idea how your brain handles that much memorization of simple numbers with pluses and minus differences. Trust me, the way I'm going to be doing these problems is the way to go. But before we actually get into that, For the first example, let's just try to rewrite an angle in terms of two angles that we would know how to handle for its trig function. This is going to be so simple, it sounds way worse than it actually is. So for A, we're going to do 15 degrees. And for these, there is not just one answer. There is absolutely not just one answer. We're just going to label one of them. I might say a second one, maybe even a third, but I'm only going to write down one. Well, I'll write down one for another. All right, 15 degrees. So what I'm trying to say is, maybe you needed to do the sine of 15 degrees, but Mr. Beckner never gave you that triangle for 15 degrees, and he didn't allow a calculator, that mean Mr. Beckner. Well, we can turn 15 degrees into a sum or difference of things involving 30, 45, 60, 90, and all the multiples and other quadrants of that. I think the easiest one would be to do 45 minus 30. I think that would be the easiest one. Now, there may be other ones that work as well, but that's the one I'm going to go with. And 15 degrees is seen a lot in this course. It's one of my favorites. Moving forward, that's not a 30 or a 45 or a 60. How about 75 degrees? How could we break this down? And again, it doesn't have to be a difference. It could be a sum. So remember, you're just trying to think about in terms of numbers like 30, 45, and 60, unless this is a really big number like 195 or maybe 225, something like that. And then you'd need to, pull out some 180s as well or 90s as well. So 45, I mean, 30 and 45, if you add those up, oops, wrong color. You get 75, so that's the answer. About 120 degrees. And when you get into quadrants 2, 3, and 4, this is where it starts becoming easier to break these down with multiple answers. Someone might say, oh, well, 75 degrees, you could say is 60 plus 15. Yes, that's true, but we don't have a triangle to manipulate 15 degrees with, so it's not the best idea. So then you could say, well, it's 60 plus 45 minus 30. And you can use this as a triple angle, but there's no formula for that, so you're going to have a dead end. All right, so 120 degrees. Well, my first instinct would be it's bigger than 90, so let me try and break this down with a 90. Well, 90 plus what would make 120? We're all good with arithmetic, I hope. 90 plus 30 would work. So that would be one way to break 120 degrees down. Or another way you could break it down without using 90, let's see, just trying to use 30, 45, and 60. Well, how about 60 plus 60? Or you could do 180 degrees minus 60 degrees. That would also work. I mean, and then there's a whole bunch more ors for this one, but that's where I'm going to stop with just 3. Now, admittedly, 120 degrees, me personally, I would never do a sum or difference formula on this one. I would say, well, 120 degrees would have a reference angle of 60 degrees, and then I just do the sine or cosine or whatever of 60 degrees, but then maybe I need a negative in the answer based on the quadrant. Quadrant 2 would say if I was dealing with sine, it'd be positive, cosine would be negative by a smart trig class. Well, maybe you're a student who's really been struggling with that as smart trig class stuff, but you're really good at memorizing longer formulas. So instead of doing what I just said, again, say I asked for the sine of 120 degrees and saying, oh, reference angle 60 degrees, sine of 60, then you use your triangle and you'll still have to use the triangles either way. And then you go, oh, okay, well, it's in quadrant 2, so it's still positive. Or if I said cosine of 120 degrees, that would be like the cosine of 60 degrees, but negative because it's in quadrant 2, again, based on the smart trig class. So the alternative approach is, oh man, I forgot all my smart trig class stuff. I can't remember it. Well, 120 is 90 plus 30 or 60 plus 60. Then you can apply whichever formula is relevant out of the blue. And you wouldn't have to worry about reference angles. You wouldn't have to worry about a smart trig class. Now, it's a longer process in my opinion, but it's another way to skin this particular trigonometric cat. That sounds terrible. No animals were harmed in the making of that poor joke. Also, what's a trigonometric cat? Cat that's really good with angles? I don't even know. I'm just being silly. Love animals. Please don't cancel me. I always try and be careful with my jokes, but I just feel like that one is a common term of phrase. So that is one of the most important aspects of trigonometry that I really have tried to emphasize so far, but now I'm going to even emphasize more. One trig problem can be done half a dozen, maybe a dozen ways. Oh, find the sine of 120 degrees. Student A does a smart trig class in reference angles. Student B does sum or difference angles. Student C does something I haven't even taught you yet. Student D maybe does student B's version, but with different numbers. There are many different angles to your approach. Horrible pun, I know. How are we on time? 7 minutes. There is no way we're going to finish example 2A in time. So let's call it a day there. I will go ahead and write down what it is. You can maybe try it on your own. So for example 2, we're just going to say evaluate. And we're going to do the cosine of 15 degrees. So here's what we're going to do next class. We're going to turn this 15 degrees into 45 minus 30. And then we'll have cosine of 45 minus 30, which means we'll need to apply one of these two formulas, whichever one is relevant, I'm not going to say. And then you'll just have a bunch of cosines of 45s, sines of 45s, cosines of 35s, and sines of, I'm sorry, I think I said 35 there, I meant to say 30. You'll just have a bunch of cosines and sines of 30s and 45s, all of which you can fall back to those two triangles with the 1, 1 square root of 2 and the 1, 2 square root of 3 with the 45, 45 and the 30, 60. And then it's just like doing 4 problems from the previous section. There we go. So try and do that on your own if you would like to. The answer will be a fraction. It'll have 2 terms in the top and 1 term in the bottom. There'll be some square roots involved, definitely. But it'll be an A plus a B over a C. And I'll even say there's 2 square root numbers in the answer, but only 2. All right, but I know probably nobody's going to do that because you're all focused on your test. Take your test. I will not give extensions on this test unless you have a legitimate doctor's note, COVID-19 doctor's note, whatever it has, or funeral note. I will not give extensions without documentation on tests in this format. I'm giving you 2 full days. Do the reviews. Again, I've only seen one person do a solid job on the review so far. The review is pivotal for the test. If you take this test before doing the review and then go back and look at the review, you're going to go, dang it, I should have done the review. Trust me. That little cheat sheet thing, which I've said several times, is not something you're supposed to have on you, but these are lots of details that will be very, very, very helpful for the test. SOHCAHTOA, your Pythagorean, your reciprocals. These 2 triangles, super, super, super critical. Knowing radian conversions, multiplying by 180 over pi or pi over 180. It's really nice to just know these off the cuff. Remember, I said on the test, I will give no problems where the entire point is to convert from radians to degrees or vice versa. And I kept my promise. So if I give you a problem like sine of 30 degrees and you put that the answer is sine of pi over 6, you literally did nothing to me. Remember to show your work. Remember to put the work in Canvas. I believe I already set up the test submission spot. It's probably gonna already booted me out, so that's okay. I got a couple minutes. Yep, I've dragged it to the top. Only thing you can see, you shouldn't see the submit final exam work because there's no green check mark. I just have that already set up. And the test 2 and test 3 work will go in there later. And you just go in there and it'll be pretty easy. Submit a file. Well, I can't show it because I'm a teacher. I can't submit a file for myself, but there's a button somewhere up here that says submit file. All right. Email me if you have any questions. Remember, you have 15 minutes to submit your file after finishing, so you need to be ready to snap pictures and upload this however you need to upload it, or scan it and upload it. I should be able to take any documents. If you have problems with it, let me know, but do not email me this work or that is to say, if you email me any of your work, I'm not going to look at it. It would just be a placeholder to say, okay, you turned it in within 15 minutes, and that's just because you couldn't get in Canvas or something like that. But absolutely 100% you have to have the work in Canvas or it doesn't get looked at. And then that's for if you want any partial credit, you can say, hey, Mr. Beckner, take a look at problems 3 and 17. I did this and this and this. I got my answer wrong, but I think I deserve partial credit. And then I can go and look at it and say, well, yes, you did actually. You did a pretty good job. Here's 4 out of 5 points. Test is 25 questions, by the way, which means each question's worth 4 points. Some questions have multiple answers to input, which means then it's just the sum of those would be 4 points. So maybe like a point each roughly. All right, have a good day. Kick this test butt. We'll see you on Monday. Take care, everybody. Work hard, make good grades.